Hello everyone, my name is Pablo Escobedo and I am a postdoctoral researcher at the University of Glasgow. Thank you very much for joining me today in this talk where I will present our work entitled Electronic Skin with Energy Autonomous Proximity Sensing for Human-Robot Interaction. My presentation is divided into four main parts. Firstly, I will start with a brief introduction to show the motivation and backgrounds of the developed work. Then I will look at the materials and methods of the work in four different aspects: the solar skin design and fabrication, the readout circuit, the communication and processing interface, and the 3D printed robotic hand. Next, I will go to the results and discussion section, where I will show the outcomes of the work in terms of energy generation and power management and proximity sensing. Finally, I will outline the conclusions of the conducted work, without forgetting to acknowledge our funders, show the reference list, and our contact information. As we are all aware, electronic skin, or eSkin, has recently emerged as a novel platform for advances in different fields such as robotics, prosthesis, health diagnostics, therapeutics, and monitoring. Among various sensing modalities for eSkin, the proximity sensing is a crucial element to enhance the interactive capabilities of robots, particularly to improve human-robot interaction. The conventional approach requires rigorous distributed sensor designs, circuits, and power supply. Energy requirement of eSkin remains a challenge as the continuous power supply through batteries is not a practical solution because they add weight, are not flexible, and requires frequent charging. Herein, we present a new approach where an electronic skin integrated on a 3D printed robotic hand consists of a distributed energy autonomous proximity sensors. The eSkin contains an array of miniaturized solar cells to generate the energy needed for infrared LED-based proximity sensors. As a proof of concept, we will show that the eSkin was integrated in an industrial robot arm to enable safe human-robot interaction. Let's turn our attention now to materials and methods, starting with the solar skin design and fabrication. The solar cells used are commercially available monocrystalline photovoltaic cells with an open circuit voltage of 550 millivolts and a short circuit current of 100 milliamperes. The cells were diced using a laser engraving machine to obtain 1 square centimeter cells. The resulting small solar cells were distributed in an array of 25 cells, which was placed as a proof of concept on the palm of a 3D printed robotic hand. Soft and flexible PDMS was used as the supporting substrate for the cells array, achieving a flexible and conformable eSkin, as you can see in the figure. Regarding the readout design and fabrication, first of all, we need to understand the working principle of the system. Basically, when any object approaches the skin, it will reflect back some radiation from the infrared LEDs to the solar cells. The variations in the cell's output current is converted to a rectified voltage, whose amplitude is related to the distance of the object that reflects the infrared radiation. To achieve this, the required stages for signal acquisition are depicted in this figure. In summary, the output current is converted to voltage through a conversion stage, after which the offset component of the signal is removed using a DC blocking capacitor. After this, the signal will be a sinusoidal waveform whose frequency is equal to the frequency of the square signal at which the infrared LEDs are driven, which in our case is 20 kHz. The amplitude of this signal increases as the object approaches the skin, meaning that more radiation is being reflected back to the solar cell. Therefore, the AC signal is rectified and filtered to obtain a constant voltage value at the output of the readout electronics. This is done by a half-wave precision rectifier. The resulting signal is then converted from analog to digital domain through the analog to digital converter input of the microcontroller. And finally, the reading is digitally processed and prepared for visualization in the PC. This leads me to the next point, which is the communication interface and digital processing. In this case, LabVIEW was used as the graphical programming interface. The microcontroller unit connects to a PC running LabVIEW by means of a USB interface, and the digitalized data from the ADC is transmitted to the PC using serial communication. To mitigate the effects of noise and errors, the raw data was filtered within the LabVIEW program. Firstly, the signal was smoothed using a medium filter with rank 2, and then the filter data went through a moving average filter. To finalize the materials and methods section, I will briefly refer to the 3D printed robotic hand. The hand and the wrist were designed with the software SolidWorks and 3D printed using PLA material. More details can be found in our previous publication, which can be found in the reference list. Let's now move to the next section, results and discussion. Firstly, we will deal with the energy generation and power management. The 25 cells in the distributed array were connected in parallel branches, and the output of the array was connected to a micropower high-efficiency solar power management module. The used module is based on an integrated circuit, which is an ultra-low power energy harvester with an embedded maximum power point tracking algorithm, a battery charger, and a power manager. It also integrates a DC-DC converter stage that was configured as a boost. So, considering the power consumption of the readout electronics, if all cells in the palm of the robotic hand were working on the maximum power point measured with the light source under study, the presented skin would generate more than twice the power required for the system operation in active mode at the highest clock rate of 100 MHz. However, there can be some scenarios where the system will not operate under these ideal conditions. For instance, not all the cells will be illuminated all the time to allow the maximum power generation. In such cases, considering the maximum power required, we would be able to operate the system using 50% of the solar cells in the palm of the robotic hand working at the maximum power point. If we operate the system at the slower clock rate, only 30% of the solar cells could be needed at this maximum power point to fulfill the power requirements of the system. A summary of all this can be seen in the table. In any case, the surplus energy generated under adequate light conditions could be used to charge a battery through the solar power management module. As previously said, the operation of the proximity sensing was based on recording the reflection of infrared radiation from the LEDs when it bounces off an object approaching the skin. When properly acquired by the readout electronics and processed by digital filtering, as previously explained, a calibration curve of the output voltage as a function of distance can be obtained, as shown in this figure. Based on this, the skin could provide the robotic hands with proximity or soft touch feedback for smarter reaction capabilities, which are needed for object collision avoidance and safe human-robot interaction. To this end, we have integrated the eSkin on a 3D printed hand onto an industrial robot arm UR5. LabVIEW was used to control the movements using real-time proximity sensing mode of the robotic arm in response to an object approaching the solar skin. Here, we can see a demonstration video where the eSkin detects the human hand approaching and reacts immediately by moving away the robotic arm to avoid a collision. In conclusion, let me sum up the main points. This work presents a flexible and conformable solar electronic skin consisting of a distributed array of solar cells in a matrix. The operating principle of solar cells is harnessed for energy autonomous proximity sensing with the use of infrared LEDs. As a proof of concept, the developed solar skin was integrated into a custom-designed 3D printed robotic hand. Under adequate light conditions, the readout electronics and sensors can be powered by the energy generated by the solar skin itself, thus becoming an energy autonomous system. In fact, the surplus of energy can be stored in batteries as a backup. Finally, a further step was taken by integrating the 3D printed hand with solar skin onto an industrial robot arm UR5 from Universal Robots. A real-time closed control loop was implemented to endow the robot arm with reaction capabilities, showing that the developed skin can operate effectively in proximity sensing mode to prevent collisions of robotic hand with approaching objects or individuals, thus opening a promising route for safe human-robot interaction. Before ending this presentation, we would like to acknowledge the Engineering and Physical Science Research Councils and the NewCam project supported by the European Union. Here, you can also find the reference list of the works cited during this presentation. And that brings me to the end of my presentation. Thank you very much for your attention, and if you have any questions, I'd be happy to answer them.